So in this course of data structures and algorithms, unit 1, we will begin with complexity analysis. So we will try to understand, I would say this concept name is complexity analysis. It is little complex to understand. So please focus and understand the concepts. What is a computational problem, right? I will just give motivation why we have to study this complexity analysis. When you write program, when you write any program, you write algorithm for that, right? You first write the algorithm, then you convert that to, you implement that to a program. Algorithm is generic. It is like in plain text or in English, whereas program can be written in any multiple programming languages, in C, C++, Java, or Python. Algorithm remains same. Algorithm is unique and same, but program implementation of that algorithm, which we call as program, may vary from language to language, right? So the goal here is, the motivation behind this complexity analysis is, we have to, when you write algorithm, we have to understand whether this algorithm is the best algorithm or not. Analyzing or understanding the complexity of this algorithm. So maybe this is the solution what you are giving. If there is a problem called sorting, if I say, if I ask you to sort a array elements, set of array elements, our one student might give approach A, other might give approach B, other person can give approach C. There are multiple ways. A single problem can be solved using multiple ways. So approach A, B, C. Among these three, which one is the best one? How, in what basis do we say it is a best one or not? Okay, so can you tell me which parameters are considered to tell that program A is better or program B is? How can we say that? Three students gave three different answers, three different no what we say, solutions or approaches for solving the sorting problem. How do you define, how do you measure that this is the best program? Yes, how do we find out that uh, time taken, time and space, right? Right. If it takes less time or less number of lines, right? Less number of lines, somebody is telling, less time, somebody is telling, less space, somebody is telling. Okay. So let's see, let's try to understand what is the actual no thing behind this question. How do we judge or justify that this approach, a particular approach is best or not? Okay. So study of that is complexity analysis. In this course, in this concept of complexity analysis, we are going to study some mathematical proofs or mathematical concept which will help us in identifying, given some certain approaches, which one is the best approach. For that, we have to understand this complexity analysis. Again, I repeat, for a given problem, there can be multiple solutions or multiple approaches, methods of solving that problem. Which method is the efficient method? How do we find out that? To find out that, we have to understand how to actually do the complexity analysis of an algorithm. So how to do that complexity analysis, we are going to study. So before we enter, we will see what is a computational problem. Okay, so computational problem means, generally problems, there are a lot of problems. How to be happy always, it's a problem. But what we are talking about, we are talking about computational problems. It means certain category of problems which requires computer, to be solved. Those kind of problems are computation problems. Okay, it's a task that computers may be able to solve. See, something like this: given a positive integer, check if the number is prime or not, or given a positive integer n, check if the number is even or not. So on, like this, we have multiple problems which requires the computer's help. Okay, such problems are computational problems. So we are going to talk about the complexity analysis of computational problems. It means problems which we are trying to solve using the help of a computer. This just an example to understand certain parameters. Take the example of sorting problem. Okay, take the example of sorting problem. What is this sorting problem? If given a set of elements, you are given array elements, like this 3 5 1 4 2. You are given this. The goal here is that you have to convert this array elements A in such a way that either they are increasing or they are decreasing, either they are increasing or they are decreasing. So you will write a algorithm, you will write a program. What is your input? Your input is an array A. Input is array A which is unsorted. What is your output? Output is again array A which is sorted. Right. So just this is just to understand some terms. Input, for every problem or every program or algorithm there is an input. For the sorting, what is the input? Sequence of n numbers. What is the output? A permutation, maybe in increasing or in decreasing order. You are arranging those numbers in increasing or decreasing order. So these terms are not new for you, input and output, because already you have solved a lot of program. What is instance of a problem? Okay, consists of the input needed to compute a solution to the problem, right? So this this is an example. Instance means an example. So for sorting, or maybe if I make it simple, for addition of two numbers program, it takes two inputs A, B, it gives one output C. This is your algorithm. But what is instance for this? Instance is, the word instance means an example input. 10 comma 20 gives 30. This is one instance. Or 20 50 is instance. 20 minus 10 is one instance. So instance of a problem means a certain input which we give. Why are we talking about instance? Because see, when we give for sorting, problem, I have an algorithm with me, some approach I have to give array as an input A. It is giving me same array which is sorted. Here it is unsorted. Okay. Now the target here is to study about the complexity, means time. Let's take about time. If I give one maybe the size of array as 10 elements, I may get the answer. If I give the same for the same algorithm, I can give 100 elements as the input, I'll get the answer. I can also give 1000 elements as the input, I'll get the answer. Will the time vary for these three, for 10, 100 and 1000? Will the time vary for those three? When I am giving 100 as the input, same algorithm, I'm giving 10, I'm giving 100, I'm giving 1000, I'm giving 10,000. Will the time taken for execution of those things will vary? This session is very, very important. Please pay attention. Please listen this. If you don't understand this, if you just go out of the this concentration, you will face difficulties. My question is, when we give different inputs for the same sorting algorithm, if I give different inputs like 10, 100 to 1000, 10,000 and so on, will the time taken for execution of that program will change or not? Okay, it is for now, you are telling it will change. Now suppose this program, this sorting algorithm, I wrote in a machine. It depends on the machine, okay. So this 10, 100,000, will it the time taken will increase or decrease? Depends on the machine. Suppose that machine is very high end machine. For that I am giving 1000. It may take lesser time than the program which I gave 10 in normal machine. It may take lesser time. 1000 may take less time in a good machine compared to a normal machine, right? That is the reason this number of inputs, that you cannot claim that the time taken for execution of a program changes with the input size. Why? Because in some machine it is machine dependent. Okay. So 1000 in a good machine I may get very quickly. 10 in a normal machine it may take more time. So we cannot claim that the number of inputs, based on number of inputs the time will increase or decrease, is a invalid claim, right? That's why we are studying about this instance of a problem. We need to understand the instance of a problem. Input size. Okay, so for sorting problem, what is the input size? The number of elements to be sorted, that is your input size, right? So a little about algorithm here. What is the term meaning of the word algorithm, right? So this is just the little information. Algos in Greek means pain. Algor in Latin means to be cold. So this none of them are actually the root word for the algorithm. From where did we get this? We get this algorithm from this no scholar of 9th century. So this was his name. Slowly it was Latinized as algorithmy, led to the term algorithm. So based on his name, we got Arab scholar, 9th century Arab scholar, we got this name algorithm. Okay. So what is his definition of algorithm, right? So step by step procedure for solving a well posed problem is algorithm. Step by step procedure to solve a problem. So what does it include? A sequence of computational steps that transform the input to output. What the algorithm does? It will convert that input to the output. And also an effective method expressed as a finite list of well-defined instructions, right? So when you write those instructions, that will be that should be the effective one. It should properly do it. And the third one, a finite set of instructions, if followed, accomplish a particular task. So ultimately, the definition of algorithm is a step-by-step procedure to solve a problem. Now, what are the different properties of an algorithm? When you write an algorithm, when you write an algorithm, you should make sure that there are you follow certain principles, you follow certain guidelines. Okay, so this is one such example. So these are the properties of algorithm. Input. So definitely some input has to be given. Zero or more quantities has to be given. Output, at least one quantity should be produced. That way we have to write our algorithm. Definiteness. Each instruction is clear and unambiguous. Okay, the instruction which you write in the algorithm should be very clear. It should not be confusing. Finiteness, very important property, finiteness. The algorithm must always terminate after a finite number of steps. What is this finite number of steps? Means when you write a program, maybe for I0, I less than n, I plus plus, I am printing here some value, percentage d comma I plus plus, something I have this kind of an no program with me, right? So this terminate after certain number of steps? It depends on n value. Finiteness means the algorithm which you write must terminate after a finite number of steps. It should not be in infinite loop. It should come out definitely after certain time. Okay, that is one very important. Sometimes you write some for loop such that it goes in infinite loop. If you make some mistake here, I greater than n, something like this, it will no go into infinite loop, right? So that should be avoided. Effectiveness. All operations to be performed must be sufficiently basic. Okay, and then in finite length, there should be in finite length. So we should write it very clearly. Okay, sufficiently basic means whatever is required for that algorithm to run is clearly given without missing any of the steps in that algorithm. So these are the properties of an algorithm. Why we are studying this? We will see how to do complexity analysis for algorithms. So computation model. Now let's try to understand. See, I am saying you have a machine M, you are working on a machine M, you are having one program or algorithm, I will say, which you are running in this machine. So you give the input, you get the output. So you are executing this algorithm in the machine M. Okay, assume if this machine follows RAM model of computation. This is one method of computation, because see, all our machines we have RAM, right? A generic one processor RAM model of computation. So like our CPU has RAM, right? If we are following RAM model of computation, in this, how does it calculates the time? Okay, how does it finds actually the time taken for running this algorithm? There can be multiple machine, like these machines can be multiple things. CPU can follow any technology, but I'm talking about RAM based computation model. Like our normal machines, all of us have RAM in that, right? We talk about RAM with the 8 GB RAM, 16 GB RAM, right? So all our machines are RAM based computation. In such RAM based computation machines, how does this works? Okay, so when you write an algorithm, step 1, then 2, 3, 4, and 5. Suppose the program which you wrote has 5 steps, right? Each instruction takes a constant time. Okay, each instruction, each step will take a constant time for execution. These are the assumptions actually. I'm talking about some assumptions. Okay, if you're executing an algorithm in a RAM based computation model machine, then these are some assumptions in that machine. It's a belief that each step will take constant time, each instruction will take constant time. Second, instructions are executed one after the another, one operation at a time, like this: first step, then step 2, then step 3, then step 4, and then step 5. Okay, this is also one assumption or a intuition in the RAM based model. Third one, loops and subroutines are not considered as simple operations. Suppose there is a for loop here, these kind of things cannot be considered as simple instructions. That is third point. Fourth, each memory access take exactly one time step. Okay, so each memory access takes exactly one time step. Means once you know, when you are storing values, this array A is the number of elements, that sorting elements if I am taking, then each one will take one step. Okay, each memory access takes exactly one time step. So when I am accessing this array, it will take one time I am going from the program, I am going to the array, it is one time, right? One, you can treat as one step. Okay, one time step we say. Under this model, running time of an algorithm is the number of steps it takes for a given problem instance. So in the RAM based computation model, when you write an algorithm like this, I will repeat once again the assumptions. This is one very important concept. What are the assumptions in RAM based model of computation? In step 1, uh, first step is that each instruction takes constant time. Okay, second one, instructions will be executed one after the other. Third one, loops and subroutines cannot be considered as simple operations. It means they will take more time. And the fourth one, each time you access the memory, it is considered as one time step. It is considered as one time step. So the running time of an algorithm, the running time of this algorithm A is nothing but the number of steps it takes for a given problem instance. So when you have an algorithm A with you, if it takes if the number of times it is accessing the memory is considered as the running time. Okay, is it clear? Any doubts here? RAM based computation model, it has some assumptions. All our machines are RAM based models. Yes, any queries? Please let me know if you don't understand, because this is one very important concept I am saying. Very important. If you are at any point of time, if you feel I'm going a little speed, or the complexity of the concept is very high, we can break it down into simple examples and understand it. Now let's find out. Let's find actually the running time. I'm talking about running time. Okay, what is the running time of an algorithm? So when you have an algorithm, what is the running time of it? It is measured based on the number of operations you are doing. Number of operations we are doing. Okay, and number of operations when we are doing, we are trying to access memory. Because if I want to do addition of this is an example, array sum. I have array with 5 elements, 1 2 3 4 5. I want to find out sum of the elements of the array. When I want to choose one, that is a of 0, it means I'm accessing memory. This variable 1 is stored in the my memory, so I'm trying to access that. Okay, so running time of an algorithm depends on number of operations, and operation means we are trying to access the memory, right? So this, you see this example, sum a n. So what is the input here? input size. What is the input we are giving here? We are giving the n. That input is n. That is number of elements. Okay, so how many times this step will happen? How many times this step will happen? It will happen. That's what we are saying. Assumption here is each instruction takes constant time. Okay, so this will take, this will be executed how many times? Step 1 will be executed one time. Next, for I equal to 1 to n, this will be executed how many times? N times. Next, s equal to s plus a of I, how many times this will be executed? This will be executed also n times. Return yes, that will be executed one time. Okay, so number of times each instruction is executed, number of times each instruction is executed, right? That is what our running time, running time, or it is also called as operations count. Operations count. Why operation count? Because how many times this operation, this is one operation, that's why one time. Here I am doing 1 to n, so n times. Okay, so operation count or running time. Okay, yes, see, for this we are talking about, see, I am talking about computation model, ram based model, computation model. Okay, all our algorithm, all our systems which we are having today, they are based on ram based computation model. In this there are some assumptions or some principles. First one, each instruction takes a constant time. Each instruction to execute one step, suppose I have an algorithm, I will write a simple algorithm here: read a, read b, then c equal to a plus b, then print c. Okay, so this is an algorithm, right? How when I run this, this is an instruction. It will how much time, how many times it will execute, how many number of times it is being executed. This will be executed one time. Therefore, this will, it will take one constant time. This will be executed. Number of times we are doing this instruction is very important. This I am doing one time. This I will be doing one time. This I will be doing one time. This I will be doing one time. So total 4 times. 4 means constant. 4 means constant time. Constant time. Okay. Number of times each instruction is repeated is the game here. So each instruction will take constant time, one time. Now, instructions are executed one after the other. After this, then this, then this, and so on. Loops, if there are loops, they are not simple operations. We should be careful when there are loops in the program. Each memory access takes exactly one time step. Okay, and we have as much memory as we need. Right? In memory, we have so much of thing, and it is one time step. This is what the important point. So now I am taking an example here. Okay, see, understand this. My point here is, given an algorithm, how many number of times each instruction is repeated will give us running time, of an algorithm. Okay, this is a simple algorithm. Array sum means given array element with 5 or n elements, find out the sum of each elements of the array. Now this is the first step. How many times will this step execute? It will happen only one time. How many times will this step execute? This will be executed n times. Also this step will be executed n times. Why n times? Because it is under for loop. No, I hope this is clear. I hope you are getting how, why it is n times. Because for loop repeats until the condition fails. Okay, so 1 to n, it will repeat that step. That step will be executed n times. Okay, and we are focusing on the running time of an algorithm. The goal is to understand the, again go back to the original question. For a given problem, you have multiple solutions. Let them be A, B, C. 3 different approaches are there. Which algorithm or which approach, which solution is the best one? To tell that, we already know that it depends on the time taken. You are saying it is time taken. Let's assume time taken for that algorithm running is the goal here. If you take that time, so we have to understand for those three solutions. I have a problem P, solution 1, solution 2, and solution C. Three solutions. We have to analyze what is the running time of this algorithm and this and this. Compare and give which one is best. Okay, so for that we are studying this complexity analysis. In that process, we have to talk about, we have to identify what is the running time of an algorithm. Student 1, roll number 1 gave A as the answer, 2 gave B, 3 gave C. Okay, we have to analyze what is the running time of each of these algorithms. How do we find out running time? Running time is nothing but number of times each instruction is repeated is the running time. Okay, some total summation of that. Okay, right. So return yes will be executed one time. If you calculate that, it is 2n plus 2, 2n plus 2 times total number of times. Okay, so 2n plus 2 times instructions are executed. Okay, so this is the running time of the algorithm. This is the running time of the algorithm. Is it clear now? How to find out running time of the algorithm? Okay, right. We have multiple examples. Let's focus more. For this util, you have matrix addition. Your input is here. You're giving two matrices A and B, each of size n cross n. Okay, let's find out what is the running time of this. How much time this particular algorithm will take for execution. Okay, in RAM based computation model, can you guess this? Can you tell me what is the running time of this particular algorithm? How much time do you think it will take? We have two for loops, and then we have one statement here. How much time does this takes? Okay, let's see. Yes, n square plus n cube, n square, right? Let's try to understand that. See, let's forget this first step, ignore this first step. Let's find out for this small thing which we have just done it before. We know this will happen n time. We know this will happen n time. We in the previous case, in the previous example we have seen that this will take n time, this will take n time, right? Based on that, I am writing here. So this will execute n time, this will execute n time. If only these two lines is the algorithm, this will be 2n. This will be 2n. Okay, right? Now, if you go back, if you add this first one also, right? I equal 1 to n. How many times this will execute? It will execute n times. It will execute n times. It means this particular block will be executed n times. How many times this is executed? 2n times. So it is n into 2n times. That is 2n square. Okay, 2n square. Again, I'll repeat once again. You ignore the first one. Take only the second and third lines. We know this will be executed n times. This also will execute n times. So the sum is 2n times. So this block will be executed 2n number of times, where n is the input size. N is the input size. That is very important. So these two lines of code will be executed 2n times, 2n number of times. Okay. Then if you include the first line here, individually this will execute n time. This will execute n time. What will this execute n time? This particular block of code will be executed n times. And this block takes 2n times. So it is n into 2n, that is 2n square. This is the running time of this algorithm, addition of two numbers. Okay, right? Next. So the important point here, complexity of an algorithm. So how do you talk about complexity? How do it depends on the resources we are using for the algorithm. Okay, complexity of an algorithm is nothing but the amount of resources required for running it. Amount of resources required for running it. We have seen the running time. But what is the complexity? How it depends on the number of resources, right? So what are the important resources? CPU time and memory. CPU time, because in CPU, I will little go into computer architecture. In CPU, we have two things: arithmetic logical unit and control unit. If I'm not wrong, in CPU diagram, if you remember, we have arithmetic logical unit and control unit, right? So actually, if you see any algorithm, if you see any algorithm, either step 1, 2, 3, 4, in any of these algorithms, if you see, either it is an arithmetic step or a logical step. In any algorithm you see, each of the steps are either it involves an arithmetic operation or it involves some logical decision making, if or for something like that. True or false, right? So CPU has ALU unit, so it requires some time, right, to do this task, to do this arithmetic operation or this logical operation in CPU. It takes some time, right? So CPU actually time taken for running an algorithm is not complexity, is not its time complexity. The CPU time is the actual one. When you have a algorithm with you, right? We just know, we saw, we discussed an example for a program. If I give the input size as 10, 100,000 and so on, if I give 1 lakh like this, right, the input size is changing, the time will change, we are saying, right? The time is not for this execution, it is the actual CPU time to execute this program. Okay, CPU time to execute the program. So two very important factors for any complexity of an algorithm are CPU time, how much time it takes in the CPU for execution, that executing that particular arithmetic or logical task, and how much memory is required, how much memory is required to help in this computation process. Why we need memory? Because I want to store the data, I want to store the input output, I want to store the input output in the memory, and from the next access it back. Okay, so all your steps when you write in the algorithm, it will go to the memory and come back. That's what we are saying, one time step. It means this is executed one time. When we say this is executed one time, means one time it is accessing memory. Okay, therefore running time is nothing but the number of times it is accessing the memory. That is the important point here. Very, very important concept, order of growth. Okay, so now the same example, for a problem P, there are two approaches, A and B. Okay, and for a given algorithm A and a given algorithm B, we know how to find out running time. We have seen how to find out running time. How to find running time? We saw these examples, right? This will execute n time, this will execute n time, this will execute one time, this will also execute one time. Therefore, it is 2n plus 2. This is the running time. Okay, here also we have identified that this is 2n square. This is the running time of this algorithm. Like that, when I have a problem, I have two solutions A and B, running time A and running time B here. Okay, how to say which one is best? You find out the running time of both. By finding running time of both the algorithms, we can say whichever is taking less time, then we say that particular algorithm is better. For example, the running time of this algorithm A is 2n square plus 3n plus 1. Running time of this algorithm B is n square, not, let me take simple one. It is 8n plus 9. Okay, these two are the running time of algorithm A and algorithm B. Now, can you tell which algorithm is best? For a problem, I have two algorithms A and B. I have calculated running time of both. I have found out running time of both, right? So for A, how to find out running time? We have seen example. When there are two algorithms with two different running times, we can compare and come to a conclusion which one is best. Okay, so here you can see, yes, this is 2n square plus 3n plus 1. So let us see which one is best. Take n is equal to 1. N is equal to 1. If you take n is equal to 1, this becomes 2 plus 3 plus 1. And this becomes 17. This becomes 2 plus 3 plus 1 is 6. Now you see, for 1, what is happening here? A is best, for n is 1. You take n is equal to 2. You need to put 2 here, 2 square 4 into 2 8 plus 6 plus 1. Again this is 15. If you take here it is 16 plus 9 25. Still here A is best. Here also A is best. Take n is equal to 3. If you take n is equal to 3, 3 square 9 18 plus 9 plus 1. So this is 28. Okay, this is 28. Here if you take 3, it is 24 plus 9. So 33, right? Again A is best. So we cannot simply say that based on by the expression 2n square plus 3n plus 1, by seeing running time alone, we cannot come to a conclusion. Okay, I'll summarize what we are seeing here. Given a program or algorithm in specific, if I am, it does not depends on the number of inputs I'm giving for the program. Okay, I'll repeat once again. Given a algorithm or a program, whatever you call, it does not depends on the number of the size of the input. Size of the input is not the game changer. That I already told you. If I give 10 in a normal machine, it may take 10 milliseconds. If I give 1000 input size in a extraordinary machine, it may take 1 millisecond. So the input size is not the parameter here. We cannot go with the size of the input. Same way, when the running time, we cannot also directly go with running time. With running time, we cannot conclude that this is 2n square plus 3n plus 1, that is A, and B is 8n plus 9. Okay, based on this also we cannot directly say that a particular algorithm is best or not, because we are saying, no, for when I give 1 this is best, when I give 2 this is only best, when I give 3 this is only best. Okay, even if I don't think, if I give 4 this will be best, right? So what is n? What is that I'm giving? What is n? N value is input size. It is input size. So when I'm giving 1 input, it is better. When I'm giving 2 inputs, it is A is better. 3 input also A is better. 4 input also A is better. Okay, so how do we come to a conclusion? The big question which we started this concept of complexity analysis is that given a problem P having multiple solutions A, B, C, how do we find out which is the best algorithm? Okay, how do we find out which is the best technique? That is complexity analysis of an algorithm. For that, we have to study a concept of order of growth. Okay, order of growth. Please pay high attention here to understand this concept of order of growth. If you understand order of growth, from here everything is easy. If you understand what is order of growth, okay, that is very important. Let's see what is order of growth. Consider two different algorithms A and B to solve a problem X. The running time of A, the notation we are using is T of n. The running time is T of n. That is number of times the instructions are executed. Okay, the running time of A is 7n square plus 8n plus 9. The running time of algorithm B is 4 into 2 power n plus 5n plus 6. Okay, so what is order of growth? Since with this example of 2n square plus 3n plus 1 and 8n plus 9, by seeing this n square we cannot come to a conclusion. Maybe this is the best algorithm, who knows? This is the taking more time. Though the running time equation looks complex and simple, we cannot conclude that. For that, to avoid this confusion, the concept of order of growth has come. Please understand this order of growth. Okay, so the rule here is that how to find out order of growth? How do you find out the order of growth? In a given running time equation, all the find out which is the higher order term here. Higher order term means n power 0, n power 1, n power 2, n power 3, n power 4, so on. In this, n power 4 is higher order. All these are lower order terms. Okay, so in this first equation, 7n square is the higher order term. So this lower order terms should be ignored. Okay, 7n square plus 8n, again 7n square, and after that any constants with that higher order term should be removed. So this becomes n square. This becomes n square. This is the order of growth for this equation. For this equation, the order of growth OOG is nothing but n square. What is the rule of order of growth? We are trying to no reduce that big equation. Maybe in some problem you may get some equation like this: 3n square plus 4n plus 7 minus 7, that's it, maybe this much. Or I may have minus 6n cube. Like this, I have one order of running time of an algorithm. Minus is not possible, but this case. And other example, I may have maybe n power 4 plus 2, that's it, n power 4 plus 2. And here I have this thing. Okay, these two are the running times of two algorithms A and B. We cannot come to a conclusion directly. Why? You verify and see. You give n as 1, you see the value. You give 2 as value, you see. You give 3 as the n value, you verify the difference. You will see that sometimes this is best, sometimes this is best. So to avoid that confusion, we have come up with the concept of order of growth. What is that? Given the running time equation, identify the higher order term, ignore or delete all the lower order terms. So 5n and 6 is deleted. After deleting those lower order terms, then delete the coefficients of the higher order term like this. So this becomes 2 power n. This becomes n square. So n square 2 power n. Which is greater here among these? Okay, which one is greater? Oh, sorry. Yeah. So we found out that for this given running time, the order of growth is n square, and for this it is 2 power n. Okay, the important observation: lower order terms and the constant coefficients of higher order terms, leading term, are insignificant. These are of no use. Okay, we need to consider only on the higher order terms, right? So order of growth running time of algorithm is n square, and order of growth is 2 power n. This you have to compare and tell which one is best. This you have to compare and tell which one is best, right? So here I have n square 2 power n. Can you tell which is which is higher and which is smaller here? Compare the order of growth. Compare the order of growth of both. Tell me which one is greater. Is this true or is this true? Which is low? Is n square low or 2 power n low? Yes. N square is low, right? Why? How do you come to such conclusion that n square is low? You may substitute some values here. You may substitute some values. If you put 1, it is 1, this will be 2. Okay. If you put 2, this is 4, this is 4. If you put 3, this is 9, this is 8. Put 4, this is 16, this is also 16. Right? If you put 5, then this is 25 and that is 32. Put 6, 6 squared 36, this is 64. Put 7, 7 square 49, this is 128, and so on. So we could see that 2 power n is higher than n square in majority of the cases. So don't simply check the lower terms. You have to go till some large value n. You have to go till some large value n. Based on that, we can compare and say that whichever is best. So the goal here is, when you have a problem P, you have 3 solutions A, B, C. For each solution, find out the running time, that is T of n. In terms of T of n is this notation for that running time. For here also you find out T of n. For this also you find out T of n. Then find out order of growth. Find out order of growth of each of them. Compare this order of growth and come to a conclusion that whichever is high or low. Okay, I hope it is clear. Any doubts till now? In order of growth, you have to find out, for an algorithm, you have to find out the running time. After finding out the running time, you have to try to avoid the lower order terms and eliminate the coefficient of the higher order term. Then you will left over with some expression, that is your order of growth. Okay, order of growth is very, very important. Let's see now different order of growth. See here, can we say order of growth of this particular program is 7n cube plus 20n log n plus 84n 30 is n cube. Why? All these are lower order terms, and this also I am ignoring. It becomes n cube. See, order of growth of n into n plus 1 by 2, n into n plus 1 by 2. If you do this, this is n square plus n by 2. So it's nothing but 1 by 2 of n square plus n. Okay, this n square I will remove. It becomes 1 by 2 n square. This is a coefficient of higher order term. I will remove this. It becomes n square. Therefore, the order of growth of this expression is n square. Now, what is given? The running time is 20. Like this, 20 is given. 20 means, I see, always we have to express the order of growth in the input size, that is n. Always you have to tell the order of growth or running time in terms of n only, you have to tell. That is the input size. Here it is 20. It is equal 20 into 1. It is 20 into n power 0. So here there are no other lower order terms. This is the only term. In that, what I have to do, I have to ignore the constant. So it becomes n power 0. N power 0 means 1. Therefore, the order of growth of 20 is 1. Okay, I'll give one more example. See, order of growth, if T of n is equal to, suppose, 1 lakh, then its order of growth will be 1 only, because it is into n power 0. This is a constant, we have to ignore. This is the only term. N power 0 is 1. So for any constant value, the order of growth is 1, whether it is 20, 30, 40, so on. Similarly, the fourth one, 3 power n plus 4n square plus 8n plus all are lower order terms compared to 3 power n. Therefore, it is 3 power n. So an algorithm is more efficient than another if its running time has a lower order of growth. Okay, so that's what we have seen. Any doubts till now? Is it clear? Previous slide, this slide you want me to explain order of growth? Which slide? Okay, so no, you have two algorithms A and B. We are trying to find out order of growth. We are trying to find out order of growth. So here in the algorithm A, this is the running time T of n. How to find running time? You have to analyze each step of the algorithm, how many times it is executing. Based on that, we got this equation. To find out order of growth of a running time equation T of n, how to do? Ignore the, find out the higher order term. This is the higher order term, because we already know that 8n is less, no, 8n is lesser than, sorry, 8n is lesser than 7n square. You put any value and see, this will be always lesser. So we are removing the lower order terms. You are left over with the higher order term 7n square. After that, ignore the coefficients of the higher order term. Okay, ignore the coefficients of the higher order term. Then you get the order of growth, right? Okay, so this is about order of growth. Now, what could be different order of growth? What could be different order of growths, right? So you may get, see, you may have such lengthy expressions. Ultimately, you may have such lengthy expressions. Ultimately, you have to convert this to only these fixed formats. Okay, so these are a few standards in order of growth. So one indicates constant order of growth. Log n means logarithmic, linear, linear arithmetic, quadratic, cubic, exponential, and factorial. So any algorithm you take, you have a problem, you have algorithms A, B, C. Any algorithm, you find out its running time, that is T of n. From that, you find out order of growth. When you have an order of growth with you, if you convert that order of growth, if you find out the order of growth, it will be definitely any one of these. Generally, most of the cases, 99% of our programs, we always get this as our order of growth. Okay, in this is the smallest one. This is the smallest one. It means program P1 has log n order of growth. Program P2 has n log n order of growth. Which is the best program here, or algorithm here, P1 and P2? Its order of growth is log n. Its order of growth is n log n. So obviously this is lesser than n log n. Log n is lesser than n log n. Therefore P1 is best. Okay, P1 is best. Suppose any particular program, its order of growth is n square, P1, and program P2 order of growth is n cube. So which is best? If someone asks you, P1 is best because it is having lower order of growth. So this is in the increasing order of their complexity. So program in complexity increases, as on when its order of growth increases. Okay, is it clear? Right, 1 then log n, then n log n, then n square, then n cube, 2 power n factorial, right? So in this way we have different order of growths. If I summarize what we have seen, we are talking about complexity analysis. In that we are talking about the what we say running time and order of growth. Given a problem P, it may have multiple solutions A, B, C and so on. For each one of them, how our goal is to find out which solution is best solution. It is clear that it does not depends on the input size. It does not depends on the input size, because program is machine independent, language independent. Okay, some machine it may perform better, some may it may not perform better. For that reason, for each of those algorithms, what we do, we try to find out the running time. We try to find out the running time like this. For each running time, we try to find out the order of growths. After finding order of growth, whichever is having the lesser order of growth, that is the best. If all three are having n square, if all three algorithms are having order of growth as n square, then all three are best solutions only. You can use any one of them. Okay, don't count number of lines. Number of lines does not define the time of the particular algorithm or program. Okay, the standard is to find out the order of growth and decide, take a conclusion on that. Okay, so with this we complete the understanding of running time and order of growth. So in the next session we will be talking about asymptotic analysis.